Okay, hello all you crazy people out there. My name is Michael, I like wizards and dragons and making games, and welcome back to making 3D games in GameMaker Studio 2 run fast. Alright, today we're talking about matrices. So in the preface video that I made about 3D optimization in GameMaker, I suggested, among other things, that there's a couple things that may be surprisingly slow when it comes to 3D games in GameMaker, and one of those things, probably the biggest one of those things that can be surprisingly slow, is dealing with matrices. I showed briefly in that video when I ran the debugger, there are a couple matrix operations that are happening in this demo with the trees here. By the way, I normally say this at the end of videos, but if you want to download this demo project for yourself and mess around with it as you're watching the video, as you're following the video, there will be a link to a GitHub repository in the video description where you can go and do that. So before I get into the weeds of how this works, I should probably just talk about the anatomy of this project real fast, just so that there are no surprises in the code. This is a sort of spin-off of the test project that I've been using for most of this 3D tutorial series. You have the ground, which is just a vertex buffer, which is tiled like this. You have the player, which is just being drawn as a cylinder, and you have about 1,000 trees, which are being drawn at random locations. So we have this should look, if you've been following my 3D series, it should look fairly familiar. We have the vertex format set up at the top. We have the grid, which represents the floor, the checkerboard grid. We're loading a couple objects from files, the player cylinder and the tree files. The trees are just hexagonally planar trees that are just being propped out of the ground with a simple tree sprite being drawn on top of them. The player is drawn pretty much immediately. The player and the ground, I should say, are drawn pretty much immediately after the camera projections are set in the camera's draw event. So this is the ground, and then right after that we have the player. The trees, their positions are randomized. There are 1,000 of them. They are randomly positioned between -2,000 and +2,000 in the world, and on both the X and Y axes. The positions of the trees are stored in this tree positions array as a struct with an X, a Y, and a Z, so much like just a regular run-of-the-mill vector struct. And those are drawn at pretty much the bottom of the camera's draw event. We are looping over the tree positions array. We are getting the X, the Y, and the Z positions from that struct data in the tree positions array. We are building a matrix for each tree. Vertex submitting the tree, we're drawing the tree using the tree sprite texture. And then we are resetting the transform with matrix build identity. And this whole thing is drawn with the basic 3D stuff shader set, which is just a spotlight that's more or less pointing at the world origin. And that's how this project works. No surprises. Anyway, back to what I was saying. This is a demo project. It's drawing about 1,000 trees individually in 3D. And it's running at an average of probably about 300 FPS real, which is definitely fast. That will definitely keep you above 60 frames per second if that is your target frame rate. But it could be better, considering that it's not actually doing all that much in the grand scheme of things. So if I were to open up the profiler, and again, if you've never seen this tool, if you run the game in debug mode and go to debugger, Windows, and profile, that will open up this window. It may be docked to the bottom by default, but you can, while the game is running, click profiling, and you can click stop profiling, and this will have the game record how long it takes your code to execute. And if you expand these sections, you can see it broken down into which individual function calls take how long to execute. And it's helpful for seeing what parts of your game are taking the most time to run, as you can imagine. When it comes to matrices, there are a bunch of matrix operations happening. The step event as a whole is taking about 3.6 milliseconds to run currently, per step and per render. That's how long a single frame takes to show up on the screen. And a big chunk of that, if you expand the camera's draw event, is in matrix build, which takes 0.4 milliseconds total to execute, which in and of itself isn't that much time. You also have matrix set, which is taking another about 0.4 milliseconds to run, and matrix build identity is about 0.35 milliseconds total. And if you add these together, it's about 1.1 milliseconds total that it takes these to run. In video editing, I will put the times in like the corner of the video so that you can keep referring back to them as I talk and change the code. But this is a decent chunk of the step event. This is about, in total, I want to say about a third of the time that it takes a frame to appear on the screen. And that's a lot, certainly. It's not like, oh my god, this one operation is taking like 90% of my frame time, but it's still a lot. And there are quite a few things we can actually do to cut that down. So let's, by the way, I said I was going to do this, but to compare on the Raspberry Pi, let me just switch the target output to the Raspberry Pi, and you'll be able to see about how well it's performing there. It's going to be much slower than on my computer here. If you've watched the introductory video to 3D optimization in GameMaker, I have gone over that in detail. Let's see. It's the same game happening on the Raspberry Pi, but much slower. You can see the debug overlay. The yellow bar is the draw event. It's taking much longer than it was on my computer, and the FPS real and average frame rates that you are seeing are taking much longer than they were on my computer. So let's jump back over here to Windows, because that's just easier to test on, and start to clean this up. So matrix build identity, that took about a third of a millisecond to do it 1,000 times. This is a function that will return the exact same thing every single time. So you really don't need to call it constantly. You really don't need to call this function constantly. You really don't need to call it at all in this particular section of code, but let's not get ahead of ourselves. Since this will return the same value every single time, we can always assign it to something like a local variable. If you want, you can just avoid the matrix build identity function entirely and just put the array literal containing what containing the values that the identity matrix is represented by. But let's we don't have to go that far.
Hey.
I don't think. Let's just save the result of matrix build identity to a local variable. This value will be the same every single time, and instead of saying matrix set, matrix world, matrix build identity, we can just use the exact value that is stored in this local variable. And if we do that, we are going to find, if I run the game in debug mode, that the frame rate is noticeably higher. So the average values is it was about 300 before, I think, maybe a little bit less, and now the average value is showing about 340 and change. And if I run the profiler again in the debugger, and I'm just going to let that run for a couple seconds so that we collect enough data for the values to average out, we can indeed see that the camera's draw event and the total frame time has gone down somewhat from about 3.6 to about 3.3 overall. And if I expand this, we can see that matrix build identity is now no longer taking 0.35 milliseconds each frame as it was before. It should be, since we are calling it far fewer times, it should be somewhere down closer to the bottom, probably, where is it, over here. It's being called 3 times per frame instead of over 1,000, and the amount of time that it takes each time is effectively 0 milliseconds, because it's nowhere near significant enough to appear on the list. So that's pretty good. We'll take that. If I were to run this on the Raspberry Pi, if I do run this in regular mode instead of debug mode, by the way, it will be slightly faster. Not by a huge amount, but you can see average FPS is about 400 instead of about, what was it before, 340. But the debugger, when it inserts its debug symbols to keep track of what's going on in your game, that is extra time that it takes the computer to update and render each frame. So if running the game in normal mode will be slightly faster inherently than running it in debug mode. And again, if I run this on the Raspberry Pi, and I realize the Raspberry Pi OS Task Manager is just sort of sitting there in the background, and I guess that could be useful if you want to see how much CPU time the game is taking up. We have gone, okay, it looks like this actually hasn't changed the output of the Raspberry Pi by a very significant amount. Okay, it's gone up a little bit, but not quite as dramatically as the version on my desktop PC did. The Raspberry Pi tends to be a little bit more GPU bound than a computer with a dedicated graphics card. much like trying to run a game on a laptop with integrated graphics or something similar to that. So that's great. We have boosted the FPS real of this project on my computer by about 100 frames per second, 100 FPS real for basically free. There's more that we can do. For example, another thing you may have noticed was that building the matrix, building the other matrix, building the transform matrix for each tree is somewhat slow. That's another 0.4 or so milliseconds per frame, which is, again, a lot. It does add up. And that's another thing that you may observe doesn't change at any point in the game between frames. This is something that's a little bit less automatic because if you have vertex buffers, if you have objects that do move around in the game, you will have to update the matrix, the transform matrix, continuously, and you won't be able to take any shortcuts with regards to not building the matrix constantly. But these trees are static. We can, instead of building the matrix every time, we can store the matrix somewhere. So, for example, if we wanted to, instead of storing a struct with an X, a Y, and a Z in the tree positions array, if we wanted to instead store the matrix itself, so we could say matrix build, random range between -2000 and +2000 on the X, random range between the same thing on the Y, 0 on the Z, because all these trees are just sitting on the ground, they're not floating up or down or anything like that. No rotation, 0 on each of the rotation axes, and a scale of 1. I'm just going to separate these onto different lines to make it somewhat easier to read. So now, instead of containing a struct with an X, a Y, and a Z, tree positions is now an array containing just arrays, those arrays being matrices, and we can, instead of grabbing the X, Y, Z positions out of the tree positions array, we can just say, this now represents a matrix. We are storing matrices in the tree positions array, and we can just matrix set that without having to spend time rebuilding it constantly. There are a couple of reasons that matrices are slow. The matrices are relatively slow in GameMaker. That was not debug mode. Let me run that in debug mode. Some of it has to do with setting them, because as I mentioned in the original video, the introduction to optimization video, setting a matrix does involve like an ass load of shader uniforms, which can take time. And also building them themselves, building matrices themselves, is quite a bit of floating point math, which doing on the CPU constantly, more often than you have to, can be quite slow. So I'm going to stop profiling. You can see that the frame time or at least the camera draw time, which is pretty much the entire frame time in this case, is now almost half of what it started with at the beginning of this video. It's 1.8 milliseconds instead of about 3.6. And you can see that many of the matrix operations are gone. Matrix build identity is no longer taking up 1/3 of a millisecond. Matrix builds for just the generic transform matrices for the entire trees are no longer taking up 0.4 milliseconds for the entire frame. It's really, the bulk of it is really now vertex submit and matrix set. Matrix set being called about 2,000 times per frame, and vertex submit being called about 1,000. The reason that these are fractional values, even though that might not really make sense to call a function like 1.5 times or something like that, is because depending on exactly what the game was doing when I clicked on the start profiling button, if it was in the middle of a frame, or if it was in the middle of a function call or something like that, it will get a little bit weird when trying to measure that. And also, if you have functions that are called a differing number of times per frame or per step or something like that, it'll take the average. If you want to see the exact values, you can uncheck the average values checkbox at the top, and we will now have whole numbers, and these values will be kind of meaninglessly large. So I like to keep the average values box checked. Anyway, we can see that we have sped things up considerably. The FPS real in debug mode is about 570 now instead of just shy of 300. So this is quite good as far as performance goes. I'm happy with this. If I were to stop this and once again run it on the Raspberry Pi, I'm not going to be using the Yo-Yo compiler, by the way. The Yo-Yo compiler can speed up your code, but that's just like generic GameMaker things, and it's not really relevant to 3D, so I won't be focusing a lot of energy on it right now. And let's see how this does on the Raspberry Pi. Okay, also granted, this is not running in debug mode either, so this will be slightly faster than it would be if it was in debug mode. But we now have the average FPS real is, it looks like upper 40s, maybe high 50s, maybe low 50s. We're getting about 50 FPS real on this project on the Raspberry Pi compared to probably, what was it, about 30 before I started changing anything. So that's pretty nice. All right, we're making this game run much more nicely than it was before. Okay, back in the land of desktop computing. So you can shave off a couple function calls here and there. If you wanted to make this a global variable, or at least an instance variable for the camera, you could make the identity matrix an instance variable for the camera. But like I said, it's currently being called so few times that reducing the number of times the identity matrix is built from, say, 3 times per draw event to just 0 if you were to cast them in the create event or something like that, really wouldn't make much of a difference. If you remember from one of the earlier times when I ran the profiler, the number of milliseconds per frame that matrix build identity is taking up now is approximately 0. So optimizing this further is really not going to be of any benefit. However, and I believe I hinted at this earlier in the video, but if I didn't, I'm doing it now. This line of code doesn't have to run at all, and going with the idea that not all function calls are created equal, doing this like extraneously won't really have that much of an effect on performance, because the game won't actually, as far as I can tell, set the relevant shader uniforms, the relevant shader matrices, unless it actually has to, which happens when you draw something, when you vertex emit something, whatever. But all the same, this is a line of code that's running 1,000 more times than it has to. Immediately after this line of code is running, where we're resetting the world matrix to the identity matrix, if the loop continues to run, the matrix just gets reset immediately the next time the loop runs without anything happening. In this line here, when we run through the loop, and if it's the last matrix set, if it's the last iteration of the loop, the next thing that happens is that the shader gets reset, and then the world matrix just gets reset anyway, right after the shader gets reset. And it's this really doesn't have any influence on what's happening in the game. If I were to remove this, you would see that the game looks exactly as it did before. It's generally considered good practice when you're drawing stuff and when you're setting like shader matrices and all that. When you're setting the draw transforms to reset the transform when you're done. But in cases like this, it is quite redundant, and removing that extraneous function call will reduce the amount of time it takes to render a frame by a slight amount. So as you can see, it's running at about 1.58, 1.6 milliseconds as for the camera's draw event, which is about 1/10 of a millisecond less than it was before. If I were to stop profiling and expand this, if you want to continue profiling while this is expanded, by the way, you can, and you'll see all the values updating in real time. But we can see matrix set is now being called 1,000 times instead of 2,000 times, and its frame time is about it's actually quite a bit lower than it was before. I think it was about 0.4 before. And the amount of time per frame that it is now taking to matrix set has gone down to 0.25 about, which is a little more than half, but it's maybe I was wrong about when I said the matrix data won't actually be submitted to the shader unless you actually draw something. That's the way it works for a bunch of the other functions that set draw state, like color and whatnot, but maybe that's not the case for matrices. Anyway, this is running much more nicely than it was before. Again, about 650-ish, I think, if you were to not account for the time that the profiler was running FPS real. On top of the debug mode generally slowing things down slightly, running the profiler also slows things down because GameMaker has to basically ask the game after every operation how long it took, which takes time. If I run the game in normal mode, you see it's gone up to about 730-ish FPS real, which is definitely much higher than it was before. It's about twice as high as it was before. It was about 300 at the start of this video. And just one more for the road. Let's run this on the Raspberry Pi and see how it does. I do have to wrap this up soon because I do have to go and like run errands after this. and I don't want this video to go on for too long. This isn't going to be a long video, I don't think, but we'll see. So this looks like if I let the values average out a little bit, we're still hitting low 50s maybe. It always takes a little longer on the first frame because it takes some amount of time for the game to start, to load the models and create the vertex buffers and all that. And that sort of drags the average down a little bit, so it helps to let the game run for a minute or so if you want really to see a good value of what the FPS reel is gonna top out at. If I were to like move the mouse around, that won't affect anything. It's not moving the mouse doesn't change the amount of operations the game has to do. It may slightly affect the number of fragments that the fragment shader has to draw, but that shouldn't be enough to really have any impact on the game's performance overall, at least not in this relatively small demo project. And it looks like high 50s is what the frame rate is now, so it hasn't gone up by quite as much as the FPS reel it has on my desktop computer, because again the Raspberry Pi is somewhat more GPU bound than a computer with a dedicated graphics card might be. But it's definitely gone up considerably from about 30 and change FPS reel to about 50. And on the subject of FPS reel not being a perfect indicator of how well your game is performing, you will notice that the regular frames per second value that is being reported on the screen is still high 30s rather than just shy of 60. And as I mentioned in the introductory video, that is because of the other things that affect frame rate that FPS reel does not account for, at least not in full, such as the GPU. All right, that's enough of that, I think. So we've boosted the performance of this game, of this demo project, by quite a bit, and all we've really done is process our matrices in a slightly more intelligent way. And by the way, I did want to at least test this because I haven't tested it. I don't think it'll really make a difference. But another value that's kind of redundant, another function call that's kind of redundant, is sprite get texture. You can see it's being called 1,000 times per update. It's not going to change. The texture of the tree sprite every time is not going to change. There's no reason for it to, but it is being called more often than it has to. It's not really affecting anything, as you can see in the profiler here. Sprite get texture is being called 1,000 times per frame, and it's only accounting for about 0.07 milliseconds per frame, and that's really quite negligible. It's about 4% of the total frame time, rounding up a little bit, and that's really not much. You can, if you want to, save sprite get texture to a local variable or an instance variable or whatever the case may be, but it's not going to doing that's not really going to make a dramatic difference. You can play around with that on your own if you want. Anyway, like I said, I do have to go somewhere after this, like approximately now. So I'm going to end this off here. If you want the code for this, again, there will be a GitHub repository in the video description containing this test project. I am not going to commit these changes because I want the at least maybe I'll commit it to another branch later. But I do want the base project to be there with the unoptimal version of drawing stuff so that you can play with it for yourself. I have a Patreon, so if you want to see more of these videos, if you want to contribute towards these videos being made, there will be links to that in all the usual places. Until then, I hope you found that interesting. I hope this allows you to think about some things that will speed up your games quite considerably. There are many other things that I will be talking about in this series. This is probably going to be a 5 to 10 video series on 3D optimization. But until then, I will see you all later. Special thanks to Kiara Elizabeth, Connor, David Key, Edward Holt, Emily Koyo, Posho, Tusk, and Zenith for supporting these videos. If you want your name in the credits or to hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.